Okay, here is the problem number 3 on the practice midterm. In this problem, we're given the cost function, which calculates the cost of manufacturing X units of a product. And we are asked to find the level of the production X for which the average cost per unit is minimized. The first step in the solution is actually indicated in the problem. We need to come up with the equation for the average cost per unit, which we denote by A of X. To obtain the average cost per unit, we take the total cost of manufacturing X units, C of X, and we divide it by the number of units, X. Now let's plug in here the expression for C of X that we're given. It's 2x squared plus 100x e to the power negative 3x, all divided by X. Now, in the numerator, we have a sum of two terms, and both of those terms need to be divided by X. So I'm going to split our fraction into two fractions, 2x squared divided by X plus 100x times e to the power negative 3x, all divided by X. Now we can make some simplification. For the first term, 2x squared over x, we can reduce this fraction by a factor of x. In the numerator, we have x squared, which is x times x, and one of those factors of x can be cancelled with the factor of x in the denominator. So basically, we're going to cross out the x in the denominator and square in the numerator. Likewise, for the second term, we have a factor of x in the numerator and we have a factor of x in the denominator. They cancel out. And so what we get is 2x plus 100 e to the power negative 3x. This function calculates the average cost per unit given the value of x. And since we are looking for the level of the production, in other words, the value of x that will minimize the average cost, we are looking for the value of x, which will make the value of this function as small as possible. Now, in looking for a minimum or a maximum of the function, the derivative of the function plays a major role. In fact, the general principle of calculus says that the maximum or minimum value of a function is achieved either at a critical point, a point where the derivative of the function is equal to 0, or at the endpoints of the interval on which we're looking for the maximum minimum value. Now in this case, we're not given any interval, and we will see later that we don't really need one because the overall maximum value, overall minimum value of this function will be achieved at a critical point. So let's go ahead and find those critical points. To find the critical points, we need to calculate the derivative of this function. Let's go ahead and calculate this derivative. And then we will set it equal to 0, and we will solve for x. So, of course, the first step is to use the sum rule. Our function is a sum of two terms, 2x and then 100 e to the power negative 3x, two terms. They're being added together, and the sum rule says that we can find the derivative differentiating term by term. In other words, we will differentiate 2x, and we will add to that the derivative of the second term, 100 times e to the power negative 3x. The derivative of 2x is just 2, right? It's the rate of change of 2x, or if you like, the slope of the line y equals 2x, that's 2. And then the derivative of the second function, here it gets a little bit complicated, a little bit more complicated, not too much, not too complicated. We have an exponential function, but the exponent is not x, it's negative 3x. So what we need to do here to calculate the derivative of this function is to use the chain rule and known derivative of an exponential function. And so what we're going to get is 100 times the derivative of e to the power negative 3x. If it were, the basic fact here to know is that the derivative of e to the power x is equal to e to the power x itself. So this is the key formula to know, a key fact about natural exponential function. Natural exponential function is the exponential function with the base equal to e. And the function that we actually need to differentiate here is not e to the power x, it's e to the power negative 3x. To get that function from e to the power x, we would have to replace x with negative 3x. And every time we do a substitution like that, in the formula for a derivative, we need to use the chain rule. Now, the chain rule says that if you're making a substitution in a formula for a derivative of a function, you can go ahead and replace x, or whatever the independent variable is, with any expression in terms of the same variable or a new variable. But after you've done the substitution, you need to multiply the right-hand side of the formula for the derivative by the derivative of what we are replacing x with. Now, in this particular case, we're going to replace x with negative 3x. So if you substitute here instead of x, let me move here. So, you know, if I simply replace in this formula, let me look at this formula right here, which gives us the correct derivative of e to the power x. I'm going to replace x, this on the left hand side, and on the right hand side with negative 3x. And so I'm going to get the derivative of e to the power negative 3x equals e to the power negative 3x. Now, if you leave it like this, the formula will be incorrect, and the chain rule tells us how to correct this. Namely, we need to multiply this right hand side by the derivative of what we are substituting for x. And in this case, we're substituting for x negative 3x, so we need to multiply this right hand side by the derivative of negative 3x. This is called the chain rule. Now, so the derivative of negative 3x is negative 3, and so the derivative of e to the power negative 3x will be negative 3 times e to the power negative 3x. Now let's go back to calculating the derivative of our function. So we've got to this point where we need to differentiate e to the power negative 3x, and we found that this derivative is equal to negative 3 times e to the power negative 3x. Okay. Now let's go ahead and substitute set it equal to 0. And now we need to solve for x. Okay, so that is an exponential equation. And the first step is to solve this equation for the exponential term, for this term here. Let me first rewrite this equation a little bit. So it's 2 minus 300 e to the power negative 3x equals 0. Let's move the exponential term to the other side. 2 equals 300 e to the power negative 3x. And so then we can actually move terms around, so we can divide both sides by 2. And also we can divide both sides by e to the power negative 3x. Doing a little bit of algebra and rearranging the terms here. These steps could be skipped, but then you would have to use properties of logarithms to simplify the answer if you don't do the simplification here first. And so then I get e to the power 3x. This is coming from e to the power negative 3x being in the denominator right here. So you see there's an e to the power negative 3x, it's in the denominator, and then 2 over 2, that's 1, so the 2's cancel out. And 1 over e to the power negative 3x is e to the power positive 3x. So you should remember from college algebra. And then, so on the right-hand side, we then e to the power negative 3x and e to the power negative 3x cancel out, and 300 divided by 2 is just going to be 150. And this is an exponential equation for x. Let's remember how we solve exponential equations. Since I don't have that much space left here, I'm going to move to the right upper corner here. So this is where we continue. E to the power 3x equals to, draw a vertical line here, 150. So the basic idea of solving exponential equations is to try to arrange for a common base for the powers that you see in the equation. The base on the left-hand side is e. The base on the right-hand side currently is 150. You can think of the right-hand side as a power, 150 to the power 1 if you like. And so the idea is to rewrite the right-hand side as a power of e. Now, by definition of logarithms, 150 is e raised to the power natural log of 150. And so what we get is e to the power 3x equals e to the power natural log of 150. And now you see the base on the left-hand side and the right-hand side of this equation is the same. The powers are the same, therefore the exponents must be the same. 3x must equal logarithm of 150, natural logarithm of 150. And so now we divide by 3 to solve for x. X will be a logarithm of 150 divided by 3. We need to spend a little bit more time thinking about what this critical point is, because what we found so far is just a critical point. We found that the function has one critical point, but this critical point could be a minimum, it could be a maximum, it could actually be neither maximum nor minimum. Let's spend a little bit of time thinking about whether this point is indeed the minimum that the problem is asking us to find. Well, so we can draw what's called a sign diagram for the derivative, which essentially refers to just the number line with the critical point marked. So let's say this is our critical point, logarithm of 150 divided by 3. And if you look at the derivative, so here's our formula for the derivative. Right here. What we know so far, since we found only one critical point, is that that derivative turns to 0 only when x equals to this value that we just found, logarithm of 150 over 3. Everywhere else, it's not equal to 0. Now the critical point divides the number line, the x-axis, into two segments, to the left of the critical point and to the right of the critical point. And these are the intervals where the derivative is either positive or negative. On each of these segments or intervals, the sign of the derivative is the same everywhere on that interval, because in order for the derivative to change sign, to go from a positive value to a negative value or vice versa, the derivative will have to go through a 0. But the only 0 of this derivative is the one that is reached at this point, logarithm of 150 over 3. So this gives us a way to check whether the derivative is positive or negative on each of these segments. We can select a test point. For example, on the left-hand side of our critical point, I will select 0 as our critical point, and then on the right-hand side we can choose some large number, let's say 100 or something like that, and we can plug them into our function. Well, the derivative, I mean. So if you substitute in 0 for x into the derivative, 2 minus 300 times e to the power 0, I'm looking at this value right here, and I'm substituting instead of x 0, so then it will turn into 2 minus 300, and that's negative, right? So we can see that, I'm sorry, I lost the file. Let me go back into it. Right. So this is where we are, and so I checked the value of the derivative at 0. I found that it is negative, and it will be negative at any other point of that interval. So negative derivative here, and that means that our function is decreasing. And then if you plug in 100, or even a larger number than that, it will be pretty clear that the value of the derivative is positive. You can use a calculator if you have, if it's hard for you to see it without a calculator. And so the function is going to go up. And so we have, this tells us that the critical point that we found is indeed the minimum point, because to the left of this point the function is decreasing, and then to the right of this function, to the right of this critical point, the function is increasing. Therefore, at this point, the function reaches its minimum value. And so, looking at the question that the problem is asking, determine the level of the production X for which the average cost per unit is minimized. The answer is that level of the production is equal to the natural logarithm of 150 divided by 3.